Hello students. Now in this video we are going to discuss the next property of the Bessel function, that is orthogonal property. So which states that if alpha and beta are two distinct roots of Jn of x equal to 0, means if these alpha and beta are the two different roots of the Bessel function Gn of x equal to 0, then we have a result integration 0 to 1 x into Jn of alpha x into Jn of beta x dx equal to 0 when alpha is not equal to beta, and the value of the integral is 1 by 2 into Jn dash of alpha square equal to 1 by 2 into Jn plus 1 of alpha whole square if alpha equal to beta. Okay, so for these two results we are going to prove, that is the value of this integral is 0 if alpha is not equal to beta. The value of the integral is 1 by 2 into Jn dash of alpha whole square or 1 by 2 into Jn plus 1 of alpha whole square if alpha equal to beta. Yes. So here Jn of lambda x is a solution of the equation. So this equation is called Bessel differential equation. So we already discussed Jn of x. For simply Jn of x, this Jn of x equal to 0, this is the Bessel function. Try to understand this point. Jn of x equal to 0, this is what? Bessel function. Then what is this Bessel function? This Bessel function is a solution of Bessel differential equation. Okay, Jn of x equal to 0 is a Bessel function and which is the solution of Bessel differential equation. Similarly, in place of x, I take lambda x. So when Jn of lambda x and it becomes the solution of Bessel differential equation. The Bessel differential equation is x square into d square y by dx square plus x into dy by dx plus, so there earlier we had x square minus n square. So as we consider lambda x, so it becomes lambda square x square minus n square into y equal to 0. Similarly, we consider other two Bessel function, that is Jn of alpha x and Jn of beta x, taking as u and v. Then for these are the Bessel functions, and this Bessel differential equations for these two are given by x square into u double dash, that is d square u by dx square plus x into u dash plus, so in place of lambda square x square we get alpha square x square minus n square into u. In place of y we have u, in place of lambda we have alpha, that is only the difference. Similarly, in place of y we have v, in place of lambda we have beta. Therefore the another differential equation is given by x square into v double dash plus x into v dash plus beta square x square minus n square into v equal to 0. These are the two differential equations for these Bessel functions. Now what we do, to this equation 1 we multiply by v by x, okay, and to this equation 2 we multiply by u by x. When you multiply by v by x, so this 1x cancelled, we left x, 1x remained here, and this v and this u double dash plus, so x cancelled, we left v here, v into u dash plus, we separate this alpha square x square into u, that 1x cancelled, then we left alpha square, this u and this v and 1x remained minus n square u square into v by x. Okay, that is minus n square uv by x equal to 0. Similarly, when we multiply by u by x to the equation 2, we get x u v double dash plus x u v dash plus beta square u v x minus n square u v divided by x equal to 0, as I explained to this equation. Okay, now these two we are going to subtracting these two equations. We take the corresponding terms from these two. I take x common, v u double dash minus u v double dash plus, from these two when we subtract, v u dash minus u v dash, again from these two taking u v x as common, we left alpha square minus beta square, so this minus term and this plus term cancelled. Okay, so these are the terms we get. Now from this first and second term, this is the product of x into v u dash minus u v dash. When you apply the product rule, the one term is x, the another term is v u dash minus u v dash. When you apply the product rule for this, we get these two. See, keeping first function x, differentiation of the second term. So this you can do some rough work. That is differentiation of v u dash minus u v dash. So you can apply the product rule for this first, that is v u double dash plus u dash v dash minus, again product rule for this, u v double dash, then minus v dash u dash. So that on simplification we get this term. Okay, first term differentiation of the second, this you can check by doing the rough work, we get this. Okay, then plus second term as it is, differentiation of x is 1. Okay, so this is the product of x into when you means d by dx of x into v u dash minus u v dash. Okay, then taking this term that side, minus that we can write as beta square minus alpha square into x u v. Okay, now what we are going to integrate both sides with respect to x between the limits 0 and 1. So integration of this derivative becomes same term, this term, that is x into v u dash minus u v dash, and the limits we are taking 0 to 1, and this beta square minus alpha square is a constant keeping outside, then integration 0 to 1 and x u v with respect to x. Next, when we take upper limit when x equal to 1, this is the term when x equal to 1, minus of lower limit becomes 0, and this term as it is. Now as we considered beginning, that is here u equal to jn of alpha x and v equal to jn of beta x. Okay, from those I am going to differentiate, that is u dash equal to, we are differentiating with respect to x. When we differentiate with respect to x, jn dash of alpha x and again into constant alpha. Okay, similarly v dash differentiation of jn is jn dash beta x, and again differentiation of beta x is beta. Okay, so these values I am going to substitute in equation 3. When we substitute, so taking v value jn of beta x, u dash is alpha into jn dash of alpha x, then minus u is jn of alpha x, then v dash is beta into jn dash of beta x for x equal to 1. Then this RHS beta square minus alpha square, integration 0 to 1 x, taking u equal to jn of alpha x and v as jn of beta x. Okay, now further we simplify as integration 0 to 1 x into, okay, from the previous page, first we are going to write this RHS integration 0 to 1. So here I wrote integration 0 to 1 x into jn of alpha x into jn of beta x dx equal to 1 divided by beta square minus alpha square. So in the previous, here in this part I am taking x equal to 1. So writing this term in the LHS, taking this term that side, and also I am taking x equal to 1 in this. when we take x equal to 1, see, when we take x equal to 1, we get alpha jn of beta jn dash of alpha minus beta into jn of alpha into jn dash of beta. So this is the result we got. Now what the next steps are, as we have a result, once alpha is not equal to beta, the second alpha equal to beta. So now first case we considering, that is alpha and beta are the different roots of jn of x equal to 0, means we are taking alpha is not equal to beta in equation 4. Okay, we have jn of alpha equal to 0 and jn of beta equal to 0, with the result the RHS 4 becomes, so this alpha jn of alpha equal to 0 and jn of beta equal to 0, because alpha is a root of jn of x equal to 0, and you know the basic, when any value of x is a root of that equation, if the value of x is a root of that equation, means that putting that value of x we are getting 0. Okay, that is a basic thing. When we take the value of x equal to alpha, alpha is a root, when you take x equal to alpha, that equation become 0. Okay, that is what we say, the root of the equation. So therefore gn of alpha equal to 0, and even beta is also the root of that equation, gn of x equal to 0, therefore gn of beta also become 0. So therefore this equation 4 becomes, so this, see, gn of beta is 0, this term becomes 0 here, and gn of alpha is also 0, so this term also become 0. So we left only this 1 divided by beta square minus alpha square, so which is not equal to 0, because beta is not equal to alpha. Thus we proved that if alpha is not equal to beta, integration 0 to 1 x into gn of alpha x into gn of beta x dx value is 0. This is the first result. Then the second result is when alpha equal to beta. Okay, now this RHS 4, this 4 equation 4 becomes when alpha equal to beta. I am going to consider alpha equal to beta. What we get when alpha equal to beta, wherever alpha is there, you can take as a beta jn of beta, this is beta jn of beta minus, sorry, into jn dash of beta minus beta jn of beta into jn dash of beta, both are same. When we take alpha equal to beta, so this term and minus of this term cancelled, so that the numerator becomes 0, and also when alpha equal to beta, so this denominator also become 0. So numerator 0 divided by denominator 0, so what we get, equation 4 becomes an indeterminate form of the type 0 by 0. Okay, when we take alpha equal to beta, the numerator becomes 0 and also denominator. Okay, when alpha equal to beta, whenever we get the indeterminate form, we apply the L'Hospital's rule. Okay, so this L'Hospital's rule we apply taking beta as a variable and alpha as a constant, or we can take vice versa. So you better take beta as a variable, alpha as a constant. Okay, keeping alpha fixed means alpha as a constant. So we take a limit on both sides, limit beta tends to alpha, integration 0 to 1 x into gn of alpha x into gn of beta x dx equal to, taking the limit. Okay, so these terms are same again. So now we are going to so here the one more condition we are using, since alpha is a fixed term, means, so as alpha is a root, alpha is a constant, when alpha is a constant, so alpha is a root of jn of alpha, jn of x equal to 0, so therefore jn of alpha is 0. When jn of alpha is a 0, okay, here is that alpha is a root of jn of x, therefore jn of alpha equal to 0. So this jn of alpha, so this term becomes 0. So what we get, only limit beta tends to alpha, alpha into gn of beta into gn dash of alpha divided by beta square minus alpha square. Here I wrote. Now to this we apply the L'Hospital's rule. So L'Hospital rule is what? We differentiate the numerator separately and denominator separately with respect to beta. Okay, when you differentiate with respect to beta, alpha is a constant. Differentiation of gn of beta is gn dash of beta, and this gn dash alpha is a constant as it is. Then differentiation of the denominator becomes 2 beta, alpha is constant 0. Okay, now so this here what we are taking alpha equal to beta. When alpha equal to beta, x into gn of alpha x, here we are taking beta as a alpha. Okay, because we are taking beta as a alpha. When beta as a alpha, so become jn of alpha x and jn of alpha x, that we can write as x into jn of alpha x whole square. Okay, both are same when beta equal to alpha. And this we are now in this, after applying the L'Hospital's rule, we are putting beta equal to alpha. Therefore 1 divided by 2 alpha, alpha jn dash of alpha, and this jn dash of alpha. Okay, then 1 by 2, this alpha cancelled, we get jn dash alpha, and jn dash of alpha is jn dash of alpha square. Okay, so thus we proved integration 0 to 1 x j n of alpha whole square, or simply we can write jn square of alpha x dx equal to 1 by 2 into jn dash of alpha whole square. So this is the one result given in the proof. Okay, and for the one more result we have, that is, okay, I just show here. This one we proved. Okay, so now we are going to prove that 1 by 2 into jn plus 1 of alpha whole square. So that we prove using one of the recurrence relation. We have the recurrence relation as jn dash of x into jn dash of x equal to n by x into jn of x minus jn plus 1 of x. Thus this is a one recurrence relation. In this we are taking x equal to alpha, jn dash of alpha equal to n by x as alpha, and jn of alpha minus jn plus 1 of alpha. Okay, from this recurrence relation we are putting x equal to alpha, since gn of alpha equal to 0, because alpha is a root of gn of x equal to 0. When gn of alpha equal to 0, taking here jn dash of alpha equal to, we get minus jn plus 1 of alpha. When we take jn dash of alpha as minus jn plus 1 of alpha, here in this I'm going to use this result. So we get the second one as x integration 0 to 1 x into jn square alpha of x dx equal to 1 by 2 into jn plus 1 alpha. That is, we get this second result. Okay, so we proved the value of this integral is 0 if alpha is not equal to beta, and also we proved that 1 by 2 into jn dash of alpha square equal to, or this is also as 1 by 2 jn plus 1 of alpha whole square if alpha equal to beta. Okay, so this is the orthogonal property of the Bessel function. Thank you.